Hello students, welcome back. We just completed section 1. Now let's begin section 2, primitive roots. Let A and M be relatively prime as usual. And the order of A modulo M is none other than phi of M, the value of the Euler-Tauschan function. Then we call A a primitive root of unity modulo M, or simply a primitive root of M. Symbolically, we can write like this. Now, we need this condition. A and M must be relatively prime, upon which entire section 1 is built. Remember, what's the first thing we did in section 1? We proved this lemma. A and M are relatively prime if and only if they exist a certain positive integer n such that a to the nth power is congruent to 1 modulo m. Equivalently speaking, the set of all such n is non-empty. Consequently, we can define the order of A modulo M as the minimum of that non-empty subset of Z plus, using the well-ordering principle of Z plus. Remember that? So we can do this if and only if A and M are relatively prime. Otherwise, nothing works. You cannot even start. So this always works, so it's nothing special. The key point is this. The order of A mod M is equal to phi of M. In general, phi of M is greater than or equal, The reason, phi of M satisfies this. A to the phi of M here is congruent to 1 mod M because of what? Remember? Euler-Fermat theorem. So phi of M is a member of this set, so it should be greater than or equal to the minimum, and the minimum is the order of A modulo M. Now that's when we looked at in view the viewpoint of phi of M. Now for given M, phi of M is fixed, and let's consider various A values given fixed M, and the order of A modulo M can reach the maximum when we hit phi of M, because it has to be always less than or equal to phi of M. But for various A values for fixed M, it may hit the maximum of phi of M for a certain A value. Then such an A value is called a primitive root of unity modulo M, or simply a primitive root of M. See the idea? The order of A modulo M must hit the maximum. M is arbitrary, but it's given a priori. It's fixed. And consequently, phi of M is already there. And we want to select various A values, various integers. Among those are relatively prime to M. And various A values give us various order of A modulo M. Among those, what's the maximum? When we hit phi of M, that's when we have the primitive root of unity modulo M, or simply primitive root of M. By the way, let's take care of some terminologies here. They can be a little bit confusing, so if it is too confusing, then just skip. But otherwise, yeah, let's do this because they are very relevant, especially for abstract algebra coming. Assume A and M are relatively prime as usual. If A to the k power is congruent to 1 modulo M, A is called a kth root of unity modulo M. Modulo M, of course, comes from this mod M, so nothing special. And what do you mean by kth root of unity? Unity means 1 in this case. For number systems, unity is 1. Number 1. Now for other more abstract algebraic structures, then unity could be something else, like identity matrix or something else. But for numbers, integers or real numbers, complex numbers, whatever, unity means 1. So kth root of 1. For example, case 2, then square root of 1. Case 3, then cubing root of 1, and so on and so forth. In general, kth root of 1. And how many are there? Well, it depends because we have mod 1. Do you recall this? Z to the k power is 1 and Z is a complex number. In that case, what is your Z? How many are there? There are precisely k of them, remember? And they're all distributed along the unit circle with the argument. The polar angle is 2k pi over n. Remember all those from pre-calculus? Those are roots of unity in complex numbers, but no mod m. Sorry about wrong key, sorry about that. I'm still having a hard time adjusting to my new computer. But here we are doing mod m, so mod m stays. Still the key is a to the k power is equals to 1. Now, in a special case, let's take the viewpoint into the order of a mod m. A to the k power is 1. Not only that, its k value happens to be the order of a mod k. Then a is called a primitive kth root of unity modulo m. That's the name. And then the order of a, the k value, happens to be phi of m. Then we call a primitive root of unity modulo m. We are leaving out kth root. Here, instead of using a primitive phi of mth root of unity, we use just a primitive root of unity because that's the maximum. If you look at it in terms of a modulo, the order of a modulo m, look at this in this viewpoint. A to the k power equals to 1, congruent to 1 mod m, means the order of a modulo m is less than or equal to k. Because of the divisibility property that we went through in section 1, this thing divides k, so that's less than or equal to k. So when do we reach the maximum? When they become equal, and that's when we have order of a is k. So we got the maximum already. And in that case, a to the k power is congruent to 1, but not only that, everything less than k, any r less than k, a to the r power is not congruent to 1. And then we get the maximum of maximum. That's when we reach phi of m. A to the phi of m power is congruent to 1, but any a to the r power less than phi of m for r, a to the r power is not congruent to 1. So if you look at it in terms of the order of a mod m, it's generally less than or equal to k, but at the maximum it reached k, so maximum here. But take the maximum again, maximum of maximum, that's when you have this. So each time we are dropping, not dropping, excuse me, kth root of unity, and we gained primitive, and next we dropped kth, so it's not definite in one direction. Okay, all right. Too much confusion. Okay, we went through the definition and some terminologies. Now let's state and prove the most important property of primitive root of unity, modulo k. So let's suppose a is a primitive root of m. Then here's the conclusion. For any integer n that is relatively prime to n, any integer n that is relatively prime to m, there exist unique r from 0 to phi of m minus 1 such that n is congruent to a to the r power mod m. That's the conclusion. So any integer relatively prime to m can be written as a to the r power modulo m. So a to the r powers will cover everything basically. And then the selection is unique, and that's actually pretty easy to see because a to whatever power, 0 power, first power, second power, up to phi of m power minus 1, they're all distinct because of that distinctness property in section 1. So if you have congruence to any one of them, there can't be another congruence to anything else because these are all distinct. So uniqueness is easy to see, but establishing the original congruence can be a bit challenging. Let's prove it. By the way, this conclusion can be re-expressed like this, alternatively using the conditional statement, because this is universal quantifier. You can always do that if you're interested, but that's just a digression. Let's come back to this and let's prove it. Because the order of A modulo m is phi of m, a to the 0 power first power up to all these, they're all distinct modulo m because of this distinctness property. Remember from section 1? These shall be all distinct because powers are all distinct mod k, mod the maximum order. And also, a to the any power is relatively prime to m because original a is relatively prime to m. So we get these two conclusions. Any a to the I power and j power, they're congruent if and only if the powers are the same. So if powers are different, then they're incongruent. So they're all distinct. So these are all distinct. And then any a to the k power from there, that's relatively prime to m. And the reason is because original is not relatively prime. Origin is relatively prime. And this one here, due to the order of a modulo m is phi of m, we can use distinctness properties. So that's why we have these two. Now on the other hand, the total of only precisely phi of m positive integers not exceeding m that are relatively prime to m, that's the definition of the Euler-Torsion function. So let us rename them R1, R2, R3 up to R of phi m. You can do that, yeah. So all positive integers 0 to m and then relatively prime to m. And then, of course, we have this distinctness because they're all coming from 0 to m, so they should be all distinct modulo m. So they're the same only when I and j are the same, the indices are the same. So we have precisely phi of m elements if you compare this set and that set, this set and that set. And then they're all distinct modulo m, and then they're all relatively prime to m, and there is no other, so they must be the same set modulo m. So select any Ri, it should be congruent to some aj, and vice versa. Select any ai power, then it's going to be congruent to some rj modulo m. So it's just a rearrangement we are looking at. Okay, we have all the preparation. Now, let's go with arbitrary n, arbitrary integer n. Then we use the division, divide by m. Then we have qm plus r. Q is quotient, r is remainder. And the remainder is from 0 to m, all right? And then we apply the Euclidean algorithm. GCD of n and m is same as GCD of r and m, and GCD of n and m is 1, so GCD of r and m is 1. So r is between 0 and m, and then GCD is 1. Oh, it's got to be one of those RIs. So it should be one of those a to the j powers. That completes the congruence. And as for the uniqueness, these are all distinct, so we cannot have two different congruences. That completes the proof.